yes. And then accept.
Okay, hi everybody and welcome. It's my pleasure to introduce Elba Alonso-Monsalve, who's going to be talking to us about primordial black holes with QCD color charge.
Thank you. Thanks so much for inviting me. It's very exciting to be here to tell you about this exciting work that I've had a lot of fun with. So this work I've done with David Kaiser at MIT, and 2 papers have come out of it so far, which you can check on the archive there. Okay, now it's responding. So the motivation for this project is the following. We thought, okay, primordial black holes may have formed in the early universe. And for those of you who for some reason are not super familiar with primordial black holes, even though they're really exciting, there are 2 main production mechanisms that we know for black holes. One is the usual one, the stellar collapse. When a star runs out of fuel, may or may not go supernova, and then if it started off being large enough, give rise to a black hole. And then there's also a primordial origin, where black holes might have formed due to gravitational collapse of overdensities in the very early universe. The second type are hypothetical, but they also have not been ruled out. And in fact, they could make up an order 1 fraction or even the entirety of dark matter, considering current constraints. Here's the current plot of where observational and theoretical constraints limit the amount of primordial black holes that could be the dark matter. Here in the y-axis is the fraction of dark matter that could be primordial black holes. And as you can see, there's a range of masses of the primordial black hole population where there are no constraints currently. So primordial black holes in this range of masses could make up the entirety of dark matter that we see today. And what Dave and I noticed is, well, the peak of the primordial mass distribution, so the most numerous mass, is actually correlated with the formation time of the black hole. It's set by the mass contained in the Hubble volume at the time of primordial black hole formation. So having this range of masses can translate into a range of times where primordial black holes would have had to form to make up the majority or the entirety even of dark matter. And that's between 10 to the minus 21 seconds and 10 to the minus 16 seconds. And then the next thing we noticed was that the QCD confinement phase transition happens when the universe was 10 to the minus 5 seconds old, which is really early, but it is way later than this range of times where primordial black holes would have formed. So the conclusion from that is that primordial black holes must have formed amidst a plasma of unconfined quarks and gluons, a quark-gluon plasma. So the natural question we asked after that is, okay, primordial black holes did form, and they'd form in that range where they could make up the majority of dark matter. Could they have formed with some non-negligible amount of QCD charge? That was the motivation, and we set to answer that question. So this talk will have 3 parts, and it's a very interdisciplinary project. So I've divided each part into a rabbit hole that will go down. If for some reason, a rabbit hole is not part of your research, you're not very excited, that's okay. If you fall asleep, no worries, because then I'll let you know when we're out of that rabbit hole, what we took away from it, and you can catch up and jump into the next one. So the first rabbit hole we'll go down is critical collapse. To understand whether black holes can form with color charge, we first have to ask, how do they form? What masses do they have? What sizes, etc. So primordial black hole formation is believed due to analytical and numerical studies to form through a process called critical collapse. So I said earlier, first there's direct collapse of overdensities to form these primordial black holes. And in order to form one, there has to be a peak in the primordial power spectrum. So it has to exceed some critical threshold, which is conservatively set to 10 to the minus 3, as you see here, for the scalar perturbations. And this is a threshold that can be realized, this peak over that threshold can be realized in realistic models of multi-field inflation, such as some of the work I cite there. And I used the word critical collapse a minute ago, because actually this process of formation is a critical process akin to the ones in statistical mechanics, where the mass of the resulting black hole is determined by a 1-parameter family of initial data, as well as a critical exponent that depends on the nature of the fluid that collapses to form the black hole. So of this one, basically, this 1-parameter set of initial data is this compaction averaged over the Hubble volume. And then if that compaction, which is a measure of the over density of really the mass contained in the Hubble volume, exceeds a certain value, then that will trigger primordial black hole formation with that mass. And if it is under that value, then primordial black hole will not form. And there are two types of critical collapse that has been identified due to numerical studies, type 1 and type 2, where type 1 has a mass gap and type 2 can allow to form black holes of arbitrarily small masses. And simulations have shown that the collapse of both perfect ultrarelativistic fluid and SU engaged fluids, engaged fields that make up fluid, are of type 2. So, and that is the case of the early universe. So we have type 2 critical collapse, and this is how the normalized distribution of masses scales. And there are two features I wanted to draw your attention to. So this in the x-axis, the mass of the primordial black holes is a fraction of the Hubble volume, and the y-axis, an axis of fraction of primordial black holes with those masses.
But what's the physics that motivates the SUN?
Oh, well, so the majority of the plasma is dominated by soft gluons, basically. So that would be the SU3 part.
Yeah.
And it's basically because they are self-interacting and bosons, so they make up the majority of the content of the universe at the time.
As well.
Yeah.
I think this whole critical collapse theory is based on spherical symmetry.
Yes.
The universe probably, I can't imagine that the fluctuations created a perfectly spherically symmetric background. So is it understood how it's modified if
Yes.
you allow variations?
Yes, so my understanding, though I'm not someone who does the numerical simulations directly, is actually, as I showed earlier, that the parameter that matters for the formation of primordial black holes is the average size of the fluctuation. So actually the way they form, I think I have a plot in my backup slides, is the entirety of the Hubble volume collapses, but as it's collapsing, it lets go of some of the mass. And that's how it's a critical process. In the end, there's only one quantity scaling, like the mass of the resultant black hole is not scaling with the volume. It ends up scaling with the size of the region that collapses, as I'll say in a minute. So the intuition that there's a perturbation and then that's what collapses is not quite right. It's more like that triggers collapse of the entirety of the Hubble volume's mass, giving rise to a black hole. And the estimates are that spherical symmetric approximation is fairly reasonable, especially for little mass black holes, which are the ones that I'll focus on right now. And I'll say that with a grain of salt because I'm not the one doing these simulations myself.
And I think some people have also seen similar critical collapse beyond spherical symmetry. Trying to form black holes with planar gravitational
It
waves.
won't be the same critical exponent.
I think they found,
Okay.
okay, there was some disagreement with different papers, but I think in the end, it's still a debate,
still
but I think
open.
they found it that it was about the same.
Okay.
Thank you,
you.
Yasu.
Comment from Dave Kaiser.
Yeah.
I'm just gonna read it, but if you wanna add more, please feel free. The most recent numerical studies have relaxed spherical symmetry and studied critical collapse within, for example, axisymmetric initial conditions. So they still have not yet studied arbitrary initial conditions, but they have continued to find critical collapse behavior upon relaxing periods.
Awesome, thank you. So what I wanted to draw your attention to in this mass distribution are two features of it. One is that there's a strong peak and a mass that scales with the Hubble volume, the mass contained in the Hubble volume. It's about a fifth of it. And please note, this is a log-log plot, so actually this peak is very pronounced. And I wanted to mention it because that is the estimate that Bernard Carr posed back in '75, way before anyone understood critical collapse. So that's pretty fun to replicate that result. And the point of interest for us is that this distribution has a long tail for masses that are smaller than the peak. So it's a polynomial tail. And that is, and again, this is all the way down to arbitrarily small masses due to type 2 collapse. So the takeaway, one of the takeaways from this section is that there's a non-zero probability to form black holes, primordial black holes of arbitrarily small masses. And the other takeaway is that this is a critical process, so all dimensional quantities have to scale with the same critical exponent. In particular, there's a length scale that we're interested in for this project, which is the size of the region of plasma that collapses to form a black hole. Like how big is the scoop of plasma of material that will end up inside the black hole? And that size also scales with the critical exponent. I will call this quantity the collapse radius, and it will come back later. So just keep in mind that this is radius does not, the mass contained in the black hole does not scale like r cubed. It actually scales like r due to the criticality of this process. And that's it for the first rabbit hole. Now we're going into QCD, because now that we know how much material falls into the black hole, we want to know how much charge, if any, is there in that amount of material that ends up inside the black hole. And for that, we need to study the quark gluon plasma. So you might remember from undergrad that charged particles undergo what's called the bi-screening. If you have, say, some charge, say a positive charge Q naught in a sea of electrons, and you try to measure the charge from some distance r, you're actually going to measure a Yukawa potential as opposed to a Coulomb potential, where the charge is screened by some characteristic length scale that's usually called the Debye length. So, of course, now we know U1, we have a SU3 theory. And to quantify these effects, what we did was construct an effective theory of soft gluons. As I said earlier, the soft gluons have occupation numbers that dominate over all others in the early universe. And so what we did was find a theory where we just integrate out the high momentum gluons and quarks, which are the next most abundant particles here, the ones that interact with the soft gluons, and find an effective theory, which we can take as in the classical limit for the soft gluons. They behave classically, and due to their large occupation numbers. And then the particles that we integrate out give rise to a current in the effective theory for the soft gluons, which I've written with the gauge potential A. They give rise to a current, which I've written as J, due to these self-interactions between the soft gluons and the high momentum gluons and the high momentum quarks. And so what we did in our first paper was find this current in curved spacetime. So just to be clear, here we have the field strength for the soft gluons, the current induced by these non-abelian self-interactions, and then there's some contribution from the fluid that's basically going to draw expansion of the universe. And actually calculating the induced current is a fun problem because thanks to our friends in the lattice community, we know that the equation of state for the hard momentum particles is actually high momentum particles. Is actually that of a non-interacting gas of particles. So rho goes like P. And that's very nice because that means that actually this hard particle dynamics can be described by classical transport equations. So, so actually we get away with doing classical mechanics for most of this. And this actually, if you did the whole, as you solve the Schwinger-Dyson equations, that's what people have shown before, that's actually akin to treating these as a non-interacting gas of particles. So we just use classical mechanics, and for those of you who've done a significant amount of Hamiltonian mechanics in the covariant formalism, these equations might look familiar. It's simply a gas of interacting or non-interacting point particles in some SU3, SUN here gauge field. And we,
Can I ask you a question?
Of course.
Just for people that are not familiar with early universe. So the effective theory is justified because the coupling is strong enough. The QCD coupling is strong enough so that, well.
It's early.
Yeah, what's the justification for the low energy selection?
well, the temperature is high, but the largest occupation numbers are those of the soft gluons.
And
Actually.
what's the
It's because of the running of the strong coupling.
yeah, so it's early in, yeah. So
It's
the
yes,
coupling is strong enough. So
exactly. And this effective theory is valid in perturbatively in the strong coupling.
I think what Elba was saying in the beginning is that if these primordial black holes would have formed, it would have been so early that it was before QCD confinement.
All right, that's right. I missed that part. Yeah, so these formed at like between 10 to the minus 21 and 10 to the minus, is when the universe was like between 10 to the 5 and 10 to the 7 GeV. So that's way earlier than 0.2 GeV. Exactly.
So Yeah, so what's that? So it's a common technique, right?
This has been a common technique indeed in flat space specifically. And so what Dave and I did was generalize this to curved spacetimes. This calculation over here. So this had been done for SUN theories in flat space and for U1 theories in curved spacetime, but no one had done it for SUN theories in curved spacetime, which is what we did in our first paper.
I'll question from the chat here. I'll just read it and then feel free to add if you want. Do these studies does these studies that go beyond the assumption of spherical symmetry find that the timescales for collapse that it's altered, or yeah, do you want to ask it actually? Turn the volume up.
Maybe the pathetic guy just rang the door.
Sorry?
Maybe the pathetic guy.
Okay, I think the question is whether the timescales for collapse gets altered or if the mass of the collapsed object.
When you relax spherical symmetry.
Yes.
I'm under the impression the answer is no, but actually I'm not super familiar with these more recent studies. So I don't know other.
I think
Just where they,
I don't think people have done axisymmetry FRW. I think all of those axisymmetry cases are asymptotically flat. So my answer is heaven.
Maybe if there's follow-up, we can.
Yeah.
But why do people do flat space if it's early cosmology?
Oh, this is referring to numerical simulations of this.
So we can't do
Process
like
of collapse.
cosmology. Yeah.
Say again?
No, but why do people do flat space if it's in the context of cosmology?
That was the first thing that people did for critical collapse. And then there's been some studies of FRW in spherical symmetry. But the axisymmetric cases where people are studying the behavior of critical collapse of GR, just because that's already quite interesting. I don't think there's been axisymmetry in FRW, I think.
All right, so back to the regularly scheduled programming. If you solve the classical transport equations for a reasonable physically motivated distribution function that solves the Hubble equation, it's a variant under Hamiltonian flow in phase space. Really fun problem in Hamiltonian mechanics if you happen to enjoy that as much as I do. And I won't take you through the details. That's paper 1, and this is about paper 2. But the result is this current, and a really exciting part of this result is that it looks qualitatively a lot like the result for a flat space, where this induced current, remember, it's multiplied by A mu. So what it's doing, it's inducing a mass on the chromoelectric component of the gauge field. And this mass is what we call the Debye mass. It looks exactly like the result for a flat space. It depends on the temperature of the plasma. But this temperature that actually shows up here is the Tolman temperature. It's a gravitationally redshifted temperature following the exact same pattern that Tolman and Ehrenfest found in the 30s. So after all this work, turns out the curved spacetime solution just amounts to promoting the temperature of the flat space result to the Tolman temperature. And here n is just the last function, like the G00 component of the metric in the ADM decomposition. That's what Tolman and Ehrenfest found. So now that we have a current J, we can solve the equations of motion for the soft gluons. And the most physically motivated solution in spherical symmetry that we're working with is that of a monopole. And the solution for this, because the induced mass only affects the chromoelectric component, is, a nice choice gauge, that it's the A0 component that gets screened, where the potential of this monopole solution is Yukawa, whereas the chromomagnetic components don't get screened, which again mimics the result from flat space. And the reason we went through all this is that what we wanted is a measure of how much charge is in the scoop of plasma that ends up inside the black hole. And so now that we have this type of solution, we have a measure of how screening works, and in particular, what is the charge that an observer would measure inside some spherical region of plasma. And now
Is
that
it electric charge or SU3,
chromoelectric, yeah.
but it looks like some of it.
It
A
looks like,
billion, like billion is a billion.
like this. equation here.
Yeah, it's like,
Okay, so what we've done is actually to find some gauge invariant measure of this is look at what E squared looks like. So given spherical symmetry, this is a quantity that we're interpreting as a charge. This is the closest thing to a nice charge. It actually matches like the Komar type integral up to a radius r.
there is a summation in there over the SU3.
Yeah. Yeah, so that's why this QR really is really square root of the trace of Q squared. So just to drive the point back home, we found the same result as in flat space, again, but with the Tollman temperature. And from now on, I will refer to this length scale, Debye length, which is 1 over the Debye mass that we found earlier. And now one more takeaway from this section is that the quark gluon plasma is neutral on long length scales, but it is not neutral to arbitrarily small length scales. And in particular, we expect deviations from color neutrality at length scales comparable to the Debye length. So in order to make a conservative estimate of how much charge there is in a spherical region of size r in this plasma, what we considered is, given some scoop of plasma, consider just one of the net color regions inside, and assume conservatively, and to make the math a little easier, that the rest of the plasma enclosed in the region is just screening that net color region at the center. So in this fashion. So then based on the equation we found before, we can estimate how much color charge there is here. That would be the Q naught from the previous equation, and then know how screening works based on the size of this region. And again, this is a bit of a conservative estimate since we're only considering the central net color region contributing and the rest of the plasma screening it. So that's it for the quark gluon plasma section. So we found in critical collapse section, for this came a little late, that black holes can form down to arbitrarily small sizes, primordial black holes. And we found what sizes, how the mass scales with the size. And then in the second section, we found an estimate for how much charge there is in the region of material that collapses to form a black hole. So now we have all the ingredients to put that together and ask, can black holes have a significant amount of QCD charge? So just to say in math what I just said in words, a black hole will have a significant amount of charge if it's, well, we found earlier, let me go step by step. The mass of the black hole scales like the radius of the region that collapses. And moreover, the peak of the mass distribution, this m bar that I wrote earlier, goes like the Hubble volume, rather a fifth of the Hubble volume. And in the second section, what we found is that to have a significant amount of color charge in some region of the plasma, we need to pick a region that's comparable to the Debye length. So in order to have a black hole with a significant amount of color charge, we want the collapse radius to be of the order of the Debye length. And we found that that scales like 1 over t. And now actually, if you plug all that into the distribution function for the masses of the black holes, you find that that scales like the temperature of the plasma, the tableau formation, over the Planck mass raised to this 1 over this critical exponent from the collapse process. And
Sorry, where did the pipelines come from here? Oh, you okay.
are you happy?
Yeah.
About that? Right, and so the dark matter window, I said it really corresponds to a particular time. That's a range of temperatures between 10 to the 5 and 10 to the 7 GeV, whereas the Planck mass is 10 to the 18 GeV. So this number is tiny, and this mu is like 0.36 for our ultra-relativistic fluid. So yeah, this is a really tiny proportion of the primordial black hole population that would have a significant amount of QCD charge. And I just really want to drive that point home, because I'm not saying that primordial black holes today, they are the dark matter, are charged or have QCD charge. That's not what I'm saying. In fact, the vast majority of primordial black holes will not have a QCD charge. They will have formed from too big a region that already would be color neutral in QCD charge. But as a byproduct, there will be a population of small primordial black holes that form alongside the bigger primordial black holes that are still around today as the dark matter. And those little primordial black holes, that byproduct, will have a significant amount of QCD color charge. So the next question is, how many really? Is this negligible or is this reasonable? And to ask a quantitative question, we consider the following. So there exist exact charged black hole solutions akin to Reiser and Nordstrom in SUN theories. And for those, there is an extremality condition, again, akin to the Reiser and Nordstrom case, given by the limit when the charge of the black hole is equal to the mass of the black hole in Planck units. And again, this would be the square root of Q squared, Ph invariant quantity. So the quantitative question we asked is, how many extremal or near-extremal colored black holes are there in the universe, or at least at the time of formation?
Sorry, maybe I missed it, but why are we suddenly into an extreme or near?
Well, we needed some sort of measure just to ask quantitatively, what is a large amount of charge? I wanted to ask which black holes have a significant amount of charge. And so to make that quantitative, now I'm asking how many of them have charge close to the extremal amount?
So the previous result was the abundance, right? The side that we showed, and that you said that it's small.
Right, exactly. It's
So
as
the
a
abundance
proportion.
is small.
Yeah, but this is an abundance kind of as a proportion of the
Okay.
entire population. So now we're asking, okay, if they are all the dark matter, then how many are actually charged, and how many can we expect to find? And so now this will become clear here. So this is the money plot of the research. So in the x-axis, I drew the temperature of primordial black hole formation. And in the y-axis, the number of near-extremal primordial black holes that were in the Hubble volume at the time of the QCD phase transition. So we could ask at any time how many black holes there are as time goes on, the Hubble volume gets bigger. But an interesting question is there a primordial black hole with a significant amount of charge at the time of the QCD phase transition? No one knows exactly how the QCD phase transition, the confinement transition happens. But if there is a black hole with an enormous amount of colored charge at that time in the universe, well, that poses interesting qualitative questions. So that's why we focus on that time. So regardless of when a black hole forms, it could be any of these temperatures, when the universe is 10 to the minus 5 seconds old, how many primordial black holes with extremal charge are there in the Hubble volume? So if primordial black holes form very early, when the universe is very hot, then we expect many near-extremal primordial black holes at the time of TQCD. And if primordial black holes form late, we expect few. And what we find is that there is at least one, the probability is not 10 to the minus 20, one, order one. If primordial black holes form when the universe was about 5 times 10 to the 7 GeV in temperature. And as I said earlier, the window for primordial black holes to make up all of the dark matter is 10 to the 5 to 10 to the 7 GeV. So this is, I would say, tantalizingly close. And considering we did lots of approximations, we did some conservative estimates, I would say this is extremely close to the dark matter window. And moreover, dark matter doesn't have to be just in that range of masses. It could be here and there. It could be a whole distribution. Yes.
This green patch,
Yes.
remind me where that comes from?
So if primordial black holes are to make up the dark matter,
Yeah.
the majority of their masses have to fall in a particular range of masses. Yes,
Okay,
given experimental and observational constraints. And that translates to times of formation because the peak of the distribution scales with the Hubble volume.
okay.
And so that's
Then you get a temperature from that.
exactly. So we know that black holes would have had to form between 10 to the minus 21 and 10 to the minus 16 seconds. And that translates
Right,
to
okay.
this range of
So
temperature.
this is the astrophysical constraints,
Exactly.
which eliminated everything else and left that little window.
Exactly, from the plot I showed in the
Fine,
beginning. So the small mass constraints actually come from not having seen Hawking radiation. And the other end of the
Or
constraints
lensing.
comes from like microlensing
Yeah.
and so on.
So then the statement is that this is consistent with n extremal being order one,
Yes,
at least if it's at the end of this window. If it's at the beginning, then it's
then it's less likely then there would be much fewer probability of having an extremal primordial black hole at the time of TQCD.
and the purple line. Did you tell us how you derived it or what?
We do have it using the ingredients that we found earlier. We calculated the mass distribution and then compare that to scale that by the number of primordial black holes we need to make up all the dark matter, essentially. And yeah, I also wanted to point out that, of course, as time goes on, the Hubble volume gets bigger, so we get more and more primordial black holes in there. Now the question is whether they still have survived or so on, but even if primordial black holes form at 10 to the 6 GeV, as time goes on, the number, if we forget about evaporation, I'll make some comments about that later, the number of extremal primordial black holes will just increase. But of course, the Hubble volume is also getting bigger, so the density is small. All right, I'll move away from the plot, and I can come back later if people have more questions. So now that we've shown that it's possible, there is at least one near-extremal primordial black hole at the time of the confinement phase transition. One might ask what happens later. And again, this is not a question we are equipped to ask quantitatively because no one knows exactly how the transition happens. But we can make some guesses. And so here is our own guess, where you can have your own, and I would love to discuss if you have any thoughts. So prior to the QCD phase transition, there's no need for the particles to form color singlets. But after the QCD phase transition, it is energetically very costly for the black holes to keep the enormous amount of charge for these near-extremal black holes. So what we think is possible is that then at the time of the QCD phase transition, just like everything else, a black hole will try to dress with particles that compensate its charge. Now you might think that would make the black hole become neutral, but actually these primordial black holes are extremely tiny. So in particular, we compare the gravitational potential and energy outside the black hole with a QCD scale to estimate how big an object with a black hole at the center and a cloud of color compensating quark gluon plasma would have to be. And we found that that object would be about 1,000 of the radius of a proton. So of course, if there's no need to have confinement inside a proton, this is still an even smaller object. So, this is not even to scale. This is the largest proton that I could fit in the slide. Again, the difference in radius would be about 1,000. So this is our proposal, or guess, that these primordial black holes would form these new objects, as like a little color neutral hadron with a black hole inside. And this would be, again, that little, and the mass would be about the mass of an elephant, which is little for black holes, but big for protons. Now, I brought up Hawking evaporation earlier because you might have some questions, like, will this black hole lose its charge in some way? That could either happen by accreting compensating charges or emitting the charges. So about accretion, the common mechanism for accretion is bond accretion, and actually that process is extremely inefficient. A black hole that starts off with a mass smaller than the sun would accrete less than 1% of its initial mass over the entire history of the universe. So these black holes have an enormous amount of charge, given that it has to be equal to their mass in Planck units. And therefore, we don't think this is an efficient enough mechanism for the black hole to lose its charge before TQCD, or even after. And then you might ask about evaporation. So there's a lot of aspects of this problem that make evaporation calculations challenging, starting by the fact that these black holes are in a medium. So most of these calculations happen for black holes that are in the vacuum. These are in a medium, and that's really important. We cannot neglect the fact that they are sitting in a very hot bath of quark gluon plasma. That was key to the formation of these black holes, and it's key to their evolution. And moreover, they are near-extremal, so that also lowers their surface gravity, which will presumably lower their Hawking temperature. But we can find a lower, all those things will make the evaporation less efficient, both the extreme near-extremality and the fact there's a hot plasma around it instead of a vacuum. But we can find a lower limit to the lifetime of these black holes by asking what would be the evaporation time of a Schwarzschild black hole with the same mass. And we found for this primordial black hole, the one that has the extremal charge at TQCD, if black holes form at like 10 to the 7 GeV. And that black hole would have a lifetime of 10 to the -4 seconds. And that's really short, but it's still 10 orders of magnitude longer than TQCD. So that leads us to say that there's no reason for this black hole to disappear or to lose its charge before the confinement phase transition. And then, to wrap up, and this is just the final slide, but this is a slide where I would love to hear from you and trigger some discussion. Here are some greater consequence, we think, of the existence of these black holes, some observational and some theoretical. So one observational consequence of these things, and again, these are things that we haven't quite calculated yet, and so there are some ideas. One is, it's hard to estimate how violent the process of dressing with color compensating charges might be. In estimating the scale of time that takes is actually quite challenging and unclear from the standpoint of QCD. But if that process is violent enough, could that form gravitational waves? Those would be of the order of the size of the black holes. They would be extremely high frequency, way more than the current observatories are tuned to detect. But it is a possible signature that could come from the early universe. Again, very faint, but is that a possible place to look for them?
But you need it to be non-spherically symmetric for that, right? Otherwise, you're not going to produce gravitational waves. So they
You
cannot-
do actually,
They cannot,
yes.
they cannot dress in spherically symmetric way. Otherwise, you're not going to produce a quadrupole. I'm not saying that's what's gonna happen. There is no reason for it to be.
Right, let's talk about it afterward though, because sorry, I haven't thought about this in a minute, but actually I think even so, there's a way. But let me check back, we wrote a couple years ago and get back to you on that. And yes, and another possibility is that if these black holes can somehow persist for a little longer than 10⁻⁴ seconds, again, that was just a lower limit in their lifetime. For example, be around when the universe was 1 second old, then they would be around during Big Bang nucleosynthesis. And so could they disrupt a bit the equilibrium of early elements? Yeah, these would be a very low density particle in our universe, these hadrons with black holes in the middle, or whatever it is they actually form. But, the equilibrium at BBN is very delicate. So could this lead to disruptions in the proportions of protons and neutrons in early elements that we could actually detect in the next few years? And let me highlight two things. One is that if we found any sort of observational evidence for these little black holes, even though they're extremely unlikely to still be around today, if we found a signature that they ever were produced, then that would be an indication that primordial black holes did form and are likely a sizable fraction of the dark matter today, since these charged primordial black holes formed as a necessary byproduct of primordial black holes as dark matter. So it's not that we're looking for charged black holes today, but if we find a signature that they were ever produced in the early universe, then that would be a signature of dark matter as primordial black holes today. And also, if we were able to find some signature of these black holes, that would be the first signature for this that would probe the small mass tail of the distribution. So I showed you earlier, the mass distribution has this shape, and actually most of the proposed observations, all as far as I know, focus on near the peak, and there is no proposed observation to probe the small tail, the polynomial tail for small masses. That's indeed how primordial black hole formation happens. So it would also be a probe of critical collapse in a way that no other observation currently, as far as I know, would be able to detect. And then moreover, there are a couple of fun theoretical questions that these black holes pose. One is implications for no-hair theorem. And actually, I think this is more related to misconceptions of the no-hair theorem that abound. And because the question is, if these black holes have a mass and have a charge, but they're screened by the medium, then from infinitely far away, I cannot distinguish a black hole that has charge from one that doesn't. I think, so that's why I say due to the presence of the screening medium. I think this boils down to the fact actually that the universe is expanding. Actually, the black holes will not be screened forever, and they will not keep their charge forever. So it's not like black holes have a hair that is not detectable from far away, that will persist forever. I think that's what makes it not violate the no-hair theorem. But I think this is a good scenario to just like question what exactly the no-hair theorem is saying, what are its limitations, and make sure we apply it correctly, because otherwise these black holes seem to contradict it.
Yeah, I think the no theorem is not really a theorem.
Uh-huh.
There are many counterexamples.
Well, someone correct me. I think it's a
But-
theorem insofar as you're very careful about what the assumptions are, right? And what its limitations are.
Yeah, I think it shrinks to the scalar Noel theorem,
Mhm.
because there are counterexamples with other types of matter. So,
Are there counterexamples for static solutions?
I think, I think so. But, not with the scalar, a static scalar solution instead. So I think it boils down to this single example of static scalar. But okay, it's not there. Okay.
Okay,
I'm
interesting. I
just,
was unaware of
I'm
not.
just saying, yeah, I'm just strengthening the point that the normal theorem may not be a problem.
Certainly, yes,
Yeah.
thank you. Yeah, so again, interesting to ask questions about the no-hair theorem and how it relates to these black holes, and no theorem's limitations. And a final theoretical question, so there could be more, and if you have any, by all means share, because we still have some time, is whether this poses any problems for cosmic censorship. So as the universe cools, the bias screening becomes less effective. And so, loosely speaking, if you ask about what's the effective charge, that is getting bigger as screening is becoming less effective. Was a real question concerns what's exactly the charge contained in a black hole and so on. But the quantitative question is, if you try to solve the Einstein equations for a metric of this type, and then you tune the bias screening to get less and less effective, the bias length getting bigger and bigger, which is what happens as the temperature decreases. Could there be a moment where, for small lambda, for small device screening, a black hole has a solution? So a black hole can form with a certain amount of charge and mass, but as screening becomes less effective, actually, there's no such a solution. There's no solution for that horizon. And that's something which we're considering these days. And, I do believe in cosmic censorship. I think it's a pretty sturdy one. So, so if we do find a violation of cosmic censorship from these black holes, I think that would raise some questions about, are we making assumptions that aren't right? Should we be more careful about how these primordial black holes form? What would be the impediment to actual violation of cosmic censorship? But nonetheless, the fact that we have this screening that is making the charge of the black hole effectively bigger as time goes on raises this question about cosmic censorship. And with these greater consequences up on the board, I will conclude my talk.
You have very interesting. You have also a great talk. I guess, cosmic censorship is about generosity in the possible form. Do you have any? Well, you were saying that there's not a lot of these primordial black holes, probably. Their number is small. Does that translate somehow to these solutions being kind of not generic? Such that, yeah, there might be violations of, I guess you're looking for weak cosmic censorship. But we know that they exist. They might just be very atypical.
I see you're saying it would, like the cosmic censorship conjecture only applies to a generic enough set of initial data.
I don't, yeah, maybe these are generic, but I just don't know.
Yeah, so they are rare, and yet the initial data is relatively generic. They
Right.
just happen to be rare in our universe.
Yeah, but you're saying like if I change the initial data a little bit, they might still form in the same way.
Yes, exactly.
So they are kind of generic.
Exactly. So in that sense, even in their
That's
little
Mhm.
small parted parameter space, they are generic.
Right.
So yeah, so I do think they shouldn't violate cosmic
Yeah.
censorship, but I don't rule out that we'll actually find that
Right.
there is no solution to the
Because
Einstein
I think the
equation.
citation that you give, most of these solutions, they go away when you impose things like the weak gravity conjecture.
Even for like the
Yeah.
with Santos paper.
Yeah, I'm wondering maybe something similar happens
Yes, in fact,
here.
that's what I'm wondering, because in this, as I said earlier, we wrote a theory of soft gluons effectively. So early on, the largest occupation numbers are gluons. So we're essentially considering that most of the black hole is made of gluons. It's possible that having neglected quarks due to their low occupation numbers actually becomes important later, because there would be the matter particle that could save this in the manner that could save things in
Right.
this paper.
Right.
So those are some of the things we're
Yeah, that's
considering
cool.
indeed.
I didn't fully understand how we derive the line of the extremal charge. The number of extremal black holes as a function of the temperature. Could you?
Yes. In this response, I'll go back. There we go.
Yeah, this line.
Yeah. So, to calculate this number, essentially, we do have a way to calculate this side over here, this normalized mass distribution related to the density of primordial black holes compared to the critical density in the universe, near the universe. And so once we calculate that, then we translate it to the number of primordial black holes by the proportion of, because it's just normalized.
Oh, right, okay.
I can give you more details.
Yeah,
I
I
just
see, I
noticed
see,
something
I see,
somewhere.
I see.
And just not, but I'm happy to talk a little more on the board if you want. It's.
Yeah.
Um,
And maybe it's not an issue for you, but there are some issues with extremal black holes that are unstable. Not sure if it would bother you because maybe you don't care exactly at extremality, you want them to have large charge.
right.
So if you're close enough to extremality, maybe that's good enough for you, but.
Yeah, so we're not realistically consider exact extremality for the formation of these black holes, and so we've done at least a linearized study of the stability of these black holes, and it seems to be stable. At
That's
least in the
extremal.
near extremal at least.
Ah,
So just like
interesting.
large,
Okay.
so at least large charge.
Yeah, near.
Because the medium could disrupt things a little bit, but it seems like they were reasonable enough.
Is there a signature if there are mergers of maximally charged primordial black holes?
I'm sure there would be if they could find each other, but they are so extremely rare. And they're not just really rare, but also before the QCD phase transition, they are screened from each other. So they're not really seeing that each other has charge because there's a lot of quark gluon plasma in between them.
But once, if they merge for gravitational reasons, then you would have this much increase in charge, right? In QCD charge.
Yes, and I just think I haven't thought about it too much because it's still extremely likely for them to find each other. Even like just to they're just so rare, the number density is
There
so
could be
small.
clustering, right? That's what many people are doing now for just standard PBHs, just assuming that they can be clustered, these fluctuations, and they form not too far from each other. Probably still very far, but.
I would suspect actually that there would need to be clustering. I do think there should not be a monochromatic population of primordial black holes. But the clustering would involve black holes of different sizes, and so that doesn't mean that in a certain cluster of primordial black holes there will be multiple with significant color charge. Because again, if there's just one at the time of when the universe was 10⁻⁵ seconds old, that means there's about one for that volume, and that's really, really low number density. So I do think that would be part of probably a cluster of other primordial black holes, but not necessarily close to other charged primordial black holes. So it could, affect how we consider. It might be worth considering interactions of a primordial black hole with significant charge with a primordial black hole that's discharged, that's bigger, things like that, but not so much collisions of primordial black holes that both have QCD color charge, or at least a significant amount. That'll be my best guess based on how rare these are.
Okay, final questions? Any questions on Zoom? Great. Well, thank you so much for.
Thank you.
Thank you.